Good morning, students. I am Dr. Tejit Singh from Shahid Bhagat Singh State Technical Campus, Firozpur, and the topic of my today's talk is thick cylinders. Now, first of all, the contents of the lecture. The first is the introduction to thick cylinders. Then we differentiate thin cylinder from thick cylinder. Then the different types of stresses produced in thick cylinders. Then we derive the Lami's formula. Now, these are the contents of this lecture. First of all, we study that what are thick cylinders. The thick cylinders are very useful in industrial use, industrial applications. There are a lot many applications of thick cylinders. For example, in industry, we have pipelines, then we have a storage tank, then the thick cylinder can be useful as a gun barrel. So, to understand the concept of thick cylinders and their use, we need to study the various theories behind this. Now, if we talk about cylinders, these are generally used to carry some fuels, gases, which are at high pressure. A cylinder can be a thin cylinder, it can be a thin cylinder, or it can be a thick cylinder. Depending upon the pressure to be resisted, we change from thin cylinder to thick cylinder. If the pressure is low, generally in the case of oxygen or air, we make use of thin cylinders. But if the pressure is very high or the fuel is very dangerous, then we make use of thick cylinder in the industry. Now, first of all, we differentiate the thick cylinder from thin cylinder. How we differentiate? On this side, we write thick cylinder, and on this side, we write thin cylinder. The first basic difference is that the classification of thick cylinder and thin cylinder, that if the ratio of d by t is less than 20, then the cylinder is classified under thick category, but if the ratio is greater than 20, then it is a thin cylinder. Now, here we can write small d as the diameter of cylinder and small t as the thickness of cylinder, thickness of cylinder wall. So, this is the first basic difference on the basis of which we classify thick cylinder and thin cylinders, that is, if the ratio of d by t is less than 20, then it is thick cylinder. If it is greater than 20, then it comes under the category of thin cylinders. Now, here we can also draw the cylinder like this. So, this is the front view of the cylinder, which is in this case closed on both the sides like this. The cylinder can subjected to internal pressure of air or gas or steam. The pressure is acting all around inside like this on all the sides. Now, let us say this is internal pressure P I. We designate the internal pressure by symbol P I. The pressure can be external. For example, if let us say the cylinder is immersed into water, then the pressure of water from outside all around is the outside pressure, like this. This is designated by PO. Now, this pressure will lead to different types of stresses inside the cylinder. So, the second classification, second difference is on the basis of stress produced. In case of thin cylinders, the stresses produced are assumed to be constant across the wall thickness. So, I write stresses are constant in case of thin cylinders, but on the other hand for thick cylinders stresses varies parabolically. Stresses varies parabolically, especially hoop stress, that is hoop stress. So, this is the second difference, that in case of thin cylinders the stresses are constant across the wall thickness, whereas in case of thick cylinders stresses vary parabolically across the wall thickness, for example, the hoop stress. Then we have third difference. So, in case of thick cylinders we have three stresses. Number 1, sigma c, it is denoted sigma c, that is hoop stress. So, due to pressure, in order to resist the pressure by the material, the stresses in three directions will produce. The first direction there is sigma c, in second direction sigma r, that is radial stress, and the third direction is, that is axial stress, that is sigma z. Now, in this case the variation of hoop stress is assumed to be parabolic. Similarly, the variation of radial stress is also assumed to be parabolic, but the variation of sigma z, it is assumed to be constant across the wall thickness. If the cylinder is very long, then the sigma z is approximately constant across the wall thickness. I show you in the diagram. But if you look for thin cylinders, we have only two stresses, that is sigma c and sigma z. So, the third stress, that is sigma r, is very small. The value of this radial stress is very small, so it is generally neglected. So, we neglect sigma r in case of thin cylinders, and we have only two stresses, sigma c and sigma z, both are assumed to be constant. Then fourth difference of applications. So, there are different applications for different types of cylinders. So, for thick cylinders I have already told that these are used as gun barrel, steam pipelines, etc., where the pressure is of the order of 400-500 megapascal. But if the pressure is low, then we can use a thin cylinder as boiler. Then we can use thin cylinder as air tank, oxygen cylinder, etc. So, these are some major difference between thin cylinder and thick cylinders. Now, let us see that what are the different types of stresses that can be produced in cylinders on the diagram. The first, we study the variation of hoop stress. The hoop stress is also known as, the second name of this is tangential stress. So, this is designated by tangential stress also, and one more name is there, that is circumferential stress. Now, due to hoop stress, the cylinder will divide into two parts. For example, if let us say if I show the top view of the cylinder, it will look like this. So, this is the top view, and if we apply pressure inside this, the pressure will look like this from top. Let us say this is P I, internal pressure. Now, due to internal pressure, the cylinder may burst. If the pressure is very large, then the cylinder will burst into two parts, and it will divide into two parts like this. It can fail from here. Let us say the cylinder can fail from like this. So, one is the upper portion of cylinder and one is the lower portion of cylinder. Now, if I show it, it can be shown in 3 dimension. First I show in 2 dimension, it will be like this. Now, in 2 dimension, the cylinder can be, the thick cylinder can be seen like this, 2 parts. Like this. So, it is divided into 2 parts in 2D, but if we see in 3 dimension, it will be more clear. So, we show over here in 3 dimension like this. Like this. So, this is the lower portion of the cylinder. After failure, the hoop stress will produced at this surface, the shaded surface on both the sides, the hoop stress will produce. Now, this stress is, if the pressure is internal, the stress is maximum at the inner surface. It can be shown by arrow like this. Then it gradually reduces in a parabolic manner like this. So, stress will reduce parabolically and become minimum at the outer surface. Similarly, at all the points, the variation of stress can be shown like this, same value at the inner surface, but it will reduce parabolically like this. Similarly, at the back surface, it will be like this. Similarly, on other side also the same variation can be seen. The same variation can be seen on the other side also, like this. At all the points, the variation of stress is parabolic, like this. But in case of thin cylinders, this variation is not parabolic, but the stress is constant at the inner surface as well as at the outer surface. The stress is same. It is denoted by sigma c. Now, in this case, at inner surface we write it is sigma c max. That is the maximum value of hoop stress at the inner surface, and at the outer surface this is sigma c min, that is the minimum value of hoop stress. So, this is the first stress, that is the hoop stress, which is the most important stress in case of thick cylinders. Now, let us see the variation of second, radial stress. Sigma r. The numeric value of radial stress is equal to the pressure applied. So, right, this is equal to the pressure applied. Now, this pressure will try to compress the cylinder and try to reduce the thickness of cylinder, but the effect of pressure goes on reducing as we move outward from the thickness. So, let us see this. If I again show the lower portion in 3 dimension. At any point I can show the pressure is acting at this point. So, we consider this point, then so this is the value of pressure or sigma r equal to internal pressure. So, sigma r try to reduce the thickness of cylinder, which is in this case T. So, if we apply pressure over here, this pressure will try to compress the cylinder. So, the effect of this sigma r goes on reducing as we move inside the thickness of cylinder. So, the value of this will be gradually reduced or parabolically reduced, we see in the subsequent derivation. If we see the effect of hoop stress, so if hoop stress, it is perpendicular to radial stress like this at one particular point. So, if we consider at inner surface, so this is sigma c, which is the maximum value sigma c max. So, both are mutually perpendicular. Then the third stress, that is sigma z. Now, sigma z is axial stress, which is also known as longitudinal stress. So, axial stress is also denoted by longitudinal stress, and this is also known as meridional stress. The axial stress will produce inside the cylinder if the cylinder is closed one. Now, if the cylinder is the open one, then the value of sigma z is 0. So, we can write that sigma z will produce only if cylinder is closed. For open cylinder, the value of sigma z is 0. Now, sigma z or axial stress, this will try to resist the pressure along the axial direction, that is along the axis of cylinder, and this will divide the cylinder into two smaller cylinders. So, let us see. For example, if let us say, so if let us say this is a cylinder, the closed from both the sides like this. Now, if the pressure is acting, I show the axis of cylinder. So, let us say this is the axis of cylinder. So, we can write axis. Now, in this case, the pressure will act along the axis, also along the lids like this, similarly like this. So, pressure is acting like this. So, this pressure will try to divide the cylinder into two parts, or the wall will resist the pressure, and ultimately the failure may take place anywhere from this. So, it will divide the cylinder into two semi cylinders. If we draw in 3 dimension, let us say I draw left hand side, this is left hand side and this is right hand side of cylinder. Now, if you show the left hand side in 3 dimension, the complete cylinder can be shown like this. Like this. this. So, on this the axis can also be shown. So, this is the axial direction, that is the axis of cylinder. Now, this stress will act along the axis on this surface. Like this. So, this is sigma z. So, on the cross section of the cylinder along the axis, the third stress, axial stress or longitudinal stress will act. You can also show in front view. Now, if we draw the front view of the right hand side, it will look like this. It will look like this. Like this. This is the axis, this failure will take place and the right hand side is shown like this. Then on the cross section we can show the stress along the axis like this, sigma z, sigma z. So, which can be shown on left hand side like this in 3 dimension, and in 2 dimension the front view of cylinder it can be shown like this, and the pressure is acting which will balance this stress like this. So, this is the variation of axial stress in case of thick cylinder. Now, let me show all the 3 stresses on one diagram, then it will be more clear. So, if we take just one half of cylinder like this, let us say I take the lower half, let us take the lower half like this, like this. So, if the cylinder is divided into 2 parts, due to the pressure applied it fails. If we show the lower half, it will look like this. Then on this cylinder, first of all I show at one particular point, I write 3 dimensional stress at a point. So, at a single point we can show, let us say at the inner surface hoop stress like this, like this. Then we show the second one, that is the radial stress perpendicular to this. So, this is sigma r, and then we show the third one, that is axial stress along the axis. So, all these 3 stresses are mutually perpendicular. So, this is sigma z along the axis. So, this is the axis of cylinder. This is axis. Along the axis we have in black color sigma z. Then along the vertical direction we have sigma c, that is hoop stress, and this horizontal, this is sigma r. So, these 3 stresses are mutually perpendicular. It can be shown separately. First sigma c, then sigma r, then sigma z. So, this is the direction of sigma c, this is the direction of sigma r, and this is the direction of sigma z. So, these 3 stresses are mutually perpendicular inside a thick cylinder when we apply the pressure. Now, the main question is that we have to determine that where the stress is maximum and where the stress is minimum. So, in order to resist the pressure, we need to know that where the value of these stresses become maximum and where the values of these stresses become minimum. So, in order to do that, we derive the Lami's formula. So, we write Lami's formula. Or Lami's equations, because we have two formulas. So, these are also known as Lami's equations. Now, to derive this, we make some assumptions. So, in order to derive the formulas, so we have some assumptions. The first assumption is that the material of cylinder is isotropic. So, material of cylinder is isotropic, that is the properties of the cylinder, properties of the material of cylinder in all the direction are same. So, material is isotropic and homogeneous. Then the second assumption, that the modulus of rigidity will remain in tension and compression. So, modulus of rigidity will be same in tension and compression. Then we take the third assumption, that is the most important, that the plane cross sections will remain plane before and after application of the pressure. That is, the cross section of cylinder, it will remain circular and there will not be any kind of crack or warpage of the cross section. So, right, the plane cross section of cylinder remains plane before and after application of pressure. Then the last assumption we take, that the strain along axial direction is assumed to be constant. So, right, the axial strain is constant. So, this will happen if the cylinder is of having very large length. If the cylinder is long, then approximately at the middle of the cylinder, epsilon z, that is axial strain, epsilon z, that is the strain along axial direction, this is assumed to be constant. So, these are the four assumptions that we take before deriving the Lami's formula. Now, let us consider a circular cylinder like this. So, if we consider the cylinder like this, let us say this is the inner surface, then we have the outer surface. The inner surface is having radius r I and the outer surface is having radius r O. The cylinder is subjected to pressure. So, let us say it is subjected to pressure of P I, then outer surface is also subjected to some pressure, let us say the pressure is P O. So, we write over here, okay, I write that is R I. R I is inner radius, R O outer radius. Then we similarly we have P I as internal pressure, and P O as external pressure.